walk with me a while? I'd love to carry you off towards something terribly old and terribly distant, and the whole night belongs to us, so let's take it slow. The thing I want to offer is the longest tale I've ever known, the account of the cosmos itself, from its earliest stirrings out to a tomorrow so remote that no living person has ever caught sight of it. Spoken not in language but in light, in gravity, in matter that gathers ever so slowly, and in time. The cosmos, as you'll come to see, refuses to hold still. It billows and turns, it lights stars and gathers them into galaxies, and starting from the simplest of openings, it patiently raises up the sort of worlds where something might one day stir awake and wonder. A few chapters here we've gauged right down to the finest detail. Others linger among the deepest riddles anyone has ever cradled. As the two of us drift along through it, I'll guide you out from those dim beginnings into the vast lattice of structure crowding the sky now, on past forces that bend where light travels, and questions I suspect we'll never quite put to rest. Right now, though, there's nothing at all for you to handle. Let your shoulders sink low. Notice how weighted your eyelids have grown. And as your thinking starts to come unknotted and slow, simply remain here at my side. Let me begin from the place where it all got its start. The opening didn't occur at one solitary point, the way a match catches in a darkened room. That image, however tempting, conceals the genuine oddness of the thing, since no shadowed room stood vacant, waiting to be set alight. From all we can presently make out, the opening played out everywhere across space together, because space itself was woven into what was playing out. Each scrap of sky you might ever take in was once compressed into the same searing, packed condition, and every heading carries that very same early past. No telescope can locate the cradle sitting off in one specific nook. Wherever it is you find yourself among the stars, the tale opens with that one ancient swelling. The middle of it isn't squirreled away inside some faraway galaxy, nor skulking past where our keenest instruments can reach. Any place you might aim your finger once belonged to that very first instant. The ground under your soles, the air against your skin, the most distant galaxy we could ever name, every one of them shares a single source. If wandering out through cosmic time with me helps the day fall away, you might let this quiet little corner know with a soft tap, or leave a kind word below for the next person lying awake under the same stars. It asks nothing of you, and it helps these slow journeys find the ones who need them. For now, though, there is nothing to reach for. Stay here beside me, and let the dark and the far light carry you onward. And space, even at this hour, keeps drawing out, ferrying the galaxies away from one another. A swelling cosmos doesn't mean the galaxies are merely racing through some unchanging void. The closer truth is odder still. The gulf between far-flung galaxies keeps broadening because the very weave lying among them is being pulled apart. A galaxy may sit nearly serene among the neighbors close by, and yet, over vast spans, the space that parts it from another swells steadily wider as the eras roll on. That's the reason remote galaxies look to be sliding away, and the most far-flung of them all seem to bolt off the fastest. They aren't hurled outward the way splinters fly from a detonation. It's closer to the entire measure of the universe shifting underneath them. Light making its way across all of that swelling space gets pulled out along its passage as well, its waves easing toward the red well before they arrive here. And that reddened glow was among the great clues that first whispered to us that the cosmos was broadening. The universe, you understand, is no stage where happenings simply take place. The stage itself keeps shifting as the tale moves along. The most ancient light anywhere still bathes the entire sky this very night. Well before any star had been kindled, the cosmos blazed with radiation of its own, trapped, a light that couldn't wander loose because charged particles kept swatting it aside over and over without end. Then a chill settled across the cosmos, and finally, electrons could fasten to nuclei and form atoms. Astronomers set this at roughly 380,000 years past the beginning, and they name it recombination, the moment when space first cleared and light could slide nearly unhindered through the broadening dark. That ancient shine remains with us still, reaching us from every heading overhead as a faint murmur of microwaves. Your eyes will never seize it, but back in 1965, a pair of scientists, Penzias and Wilson, chanced upon it as a stubborn static in their antenna. An infant's portrait of the universe snapped before one lone galaxy had taken shape. The faintest ripples across its warmth flag where matter once pooled a touch more densely, and those slight gaps later ballooned into the mightiest structures there are. Every one of us is swaddled in that afterglow of the newborn cosmos, a fossil light more ancient than any star we shall ever lay eyes on. Nearly all of what's out there, as it happens, never turns up in our telescopes. The stars and planets, the wandering gas, the luminous galaxies we behold are merely a thin shaving of everything that seems to be on hand. One slice of the remainder is dark matter, which neither glows nor drinks in light in any familiar manner, and yet betrays itself through its tug. Lacking it, galaxies wouldn't wheel the way they do, and the great clusters wouldn't grip one another so tightly. A further, still larger slice is dark energy, our stand-in label for whatever hidden thing seems to be rushing that expansion onward. Back in 1998, astronomers studying remote bursting stars grasped, much to their astonishment, that the spreading wasn't easing off, but softly gathering speed. And dark energy became the name we pinned on that puzzle. Taken together, these hidden parts steer the universe across its grandest scales. And none of this renders them make-believe. We merely detect their presence in effects that ordinary matter could never account for. The humbling fact is that we've mapped staggering beauty across the heavens, and still the greater part of all that exists keeps clear of us, the lit face of a far deeper enigma. Every atom settled inside you, I really ought to tell you, was molded ages ago within ancient stars. The young cosmos turned out next to nothing beyond hydrogen and helium, never plenty enough to craft bone or blood or one living cell. The weightier ingredients came together afterward, far down inside stars, and were turned loose when those stars perished. Carbon was lit within aging stars, oxygen spilled out of the massive ones, and iron took shape in the closing chapters of a star's life and in its furious finale. The scarcest elements of all, the gold, spun into legend, called for true cosmic fury to come into being, the detonation of a supernova or a pair of neutron stars smashing together. Down the eras, dying stars hurled all of this material back into the dark, sowing the very clouds that would someday tumble together into fresh stars and planets, and our own solar system drew itself up out of such recycled grit. The calcium stiffening your teeth, the iron coursing your blood, the carbon threaded through your cells. Not a bit of it is purely earthly. It is ancient stellar handiwork, assembled long before the Earth was around, then gathered into a body that can lie here and softly marvel at the place it sprang from. There are spots out there as well where time itself eases off. Come near a black hole and gravity turns so savage that it reshapes the very tempo of time. This is no versifier's flourish. It tumbles right out of general relativity, which showed us that gravity and time's passing are tied to one another. To anyone looking on from a secure remove, a clock let down toward the rim would appear to tick slower and slower, and the closer it stole toward that boundary, the more the effect would mount. And yet for the clock on its own, time would feel utterly normal, since everything in its vicinity would slacken right along with it. That divide between the two onlookers tells us time is no universal drumbeat ringing out the same in every place. It bends along with gravity, with motion, with the spot where you happen to stand. That outer rim around a black hole isn't a solid barrier, but it traces the line beyond which nothing can scramble back out, and where time itself holds to a different beat. Let me bear you back once more, to a time when the universe was flatly too hot for atoms to keep together. In its earliest stretch, nothing we would know as ordinary matter was around yet. Only a scorching stew of particles and radiation, so brimming with energy that no atom could endure, with electrons tearing about freely rather than nesting around any nucleus. Nothing yet had been sorted into stars or planets or chemistry of any sort. It lay nearer to a dazzling, crowded plasma, governed by heat and unending collision. Only as the universe unfurled did its temperature sink far enough for steady atoms to come into form, and that gradual chilling reworked everything that came after. With electrons finally nestling around their nuclei, light was loosed to pour outward, and gravity could set about, patiently, to gather matter into the structures still waiting to be born. Let me sit beside you a while in the quiet, and turn over the question of how all you know came to exist. Hold this softly in mind. The world we love leans, top to bottom, on one tender shift in the deep past. Lacking atoms, nothing could become a molecule. Lacking molecules, there would be no stone, no sea, no breathable sky, no living cell. This familiar place only arrived once things had chilled enough that matter could settle into forms built to endure. Even tonight, the great islands of stars go on quietly feeding. Through a telescope, a galaxy can look entirely serene, a motionless pool of light, and yet its story is most often written in seizure and soft undoing. The larger ones swell by gathering up nearby companions, hauling them close on gravity alone. When a smaller galaxy slides inward, the tidal pull of that bigger system thins it out, spooling its stars into long ribbons that loop and trail about the giant. Such pale threads resemble marks pressed into the earth of an old village, a tale held in starlight. They whisper to us that no galaxy is ever truly done. Each is assembled gradually, fragment upon fragment, over stretches of time so vast the mind can only lean toward them. Our own Milky Way has already devoured smaller galaxies, and even now it keeps tugging and worrying at little dwarf companions. Picture it gently. This is almost never a smashing of one star into another. So broad and so empty is the space within a galaxy that its stars themselves seldom meet. Gravity merely reshuffles their unhurried orbits, stirs the gas about, and recasts the entire drifting shape. And so a galaxy is more than a throng of suns. It is a sort of remembering of all it has ever taken into itself. And someday, far beyond us, our Milky Way and the enormous galaxy called Andromeda are expected to draw together and gradually merge, roughly 4 or 5 billion years ahead, 2 cities of stars pouring into a single one. Let me carry you a step further onward, toward a future that may prove dark and cold and endless. Cosmologists puzzle not only over our origin, but over where the whole of this is drifting. The evidence we can gather hints that the expansion will simply keep going, and that the far galaxies will float ever more distant from each other over stretches of time past reckoning. Fresh stars may grow scarcer as the gas is spent or sealed away. The hottest, most brilliant suns gutter out soonest. Tiny red stars can burn for nearly forever, and yet even those dim away in the end. Galaxies may crowd with the hushed remnants of stars, faint cooling worlds, wandering black holes, cold ash. And should the expansion keep picking up speed, the distant stretches of the cosmos may drift past reach for good, leaving each surviving clan of galaxies lonelier and lonelier in the dark. That slow finish often goes by the name heat death, though no fire lives inside it. It is merely the soft ebbing of usable energy, of warmth and of contrast. The cosmos would not close in one abrupt moment. It would keep thinning and chilling and easing, bearing time forward into something nearly beyond imagining. Now lift your eyes with me, for the sky offers us a look backward across billions of years. Astronomy is a patient sort of time travel, since light is never quick to reach us. Glancing up at the moon, you behold it as it stood a heartbeat past. When telescopes swing toward the closer stars, they take them in as they were years earlier. And as they collect the dim shine of distant galaxies, they are decoding letters sent off while the universe was still very young. That is the reason a deep picture of space doubles as a sort of aged record. A faraway galaxy is never given to us as it stands now, but only in the guise it wore back when its light first departed on that long journey. The deeper out we strain to see, the earlier the page we are flipping to. Our finest observatories can examine galaxies older than both Sun and Earth, a few from close to the very first dawn of galaxy making. The James Webb Telescope has been peering into that early dark and turning up galaxies startlingly bright and mature for so young a cosmos, a small riddle that astronomers are still mulling. So the night sky amounts to far more than merely a long look outward through space. It is a storehouse stacked in layers of cosmic history, where each lone mote of light bears a little timestamp from wherever it set out. Let me draw you the whole way back now, to where space and time first began. That worn phrase, the Big Bang, can make it ring like a detonation touched off inside some patient void. The true notion runs quieter and far odder. It tells of a first condition when the universe was beyond imagining hot, dense, and rapidly billowing outward. Space was no crate perched outside the happening. Time was no separate clock already counting off somewhere past it. By our best grasp of it, space and time are threaded into the very weave of the universe, and the earliest instant we can name marks the rim of what our models managed to touch. To wonder what stood before may not even carry a clear sense, since ordinary time may fail to reach tidally across that boundary. The expansion we can follow backward with genuine confidence right to ferociously early conditions. And yet that absolute first instant stays knotted up with riddles about gravity and the quantum realm we have not solved. So the Big Bang stands as both a mighty account and an open door, showing us how the universe we can watch rose from a hot start while still gesturing toward deeper things still beyond our knowing. Linger with that idea one moment more, here in the dark. We are prone to picture time as a line that runs back without end. Cosmology softly unsettles that hunch. If time belongs to the same weave as space, and that weave was once compacted into a strikingly tight early condition, then imagining any moment preceding the start turns wonderfully slippery to grip. A few thinkers suspect that time itself merely came up alongside the expansion. By that picture, no earlier clock stood waiting for things to occur, no blank reach of duration perched outside the whole of it. The start would be the birth of the very scaffolding by which before and after come to mean a thing at all. None of this declares the mystery shut. Physicists keep roaming through notions of quantum gravity, of rebounding universes, of stranger architectures lying beneath ordinary time. Yet even the bare chance of it is enough to steal your breath. That steady current you sense in your own pulse, this very moment, may share in the same unfolding that fashioned the galaxies. Time may be no backdrop whatsoever. It may rank among the oldest things the universe has ever fashioned. And the just-born cosmos was tinier than any single galaxy you might name now. In those first moments we can sensibly talk about, the entire region destined to become all we can see was pressed into a state of staggering heat and density. It was no little ball adrift within some roomier space. Instead, every bit of space destined one day to unfurl into the universe we can see sat once packed far tighter than it lies today. Setting that beginning beside a galaxy is nearly a cheat, since galaxies turned up far later, but the comparison still lets the mind grope toward the scale of it. Across a broad and gleaming disk, the suns of our Milky Way now spread themselves. Yet every scrap of matter and of space, bound up with the horizon we can reach, set out from something unbelievably hotter and smaller. Out of that dense kernel, the expansion bore regions apart, let the heat drop away, and let structure form one careful step after another. Everything immense we know rose up out of something nearly impossibly small. There may also have come a lone, astounding instant when space pulled itself wider, faster than light does. Among the boldest ideas in the whole of cosmology is the thought that the infant universe passed through a vanishingly short burst of growth. In that flash, space may have ballooned at a pace past all reckoning, ironing out the entire cosmos and dragging the faintest ripples wide across enormous distances. None of this snaps the rule that nothing may travel through space faster than light, because that rule speaks to movement through space, while here, it was space itself doing the stretching. The idea helps make sense of why the universe appears so even, so much of a kind, in places set too far apart to have ever swapped signals the ordinary way. It supplies a reason, too, for how microscopic flickers could ripen into the first patterns for all that came after. This early ballooning has not been nailed down in every detail, and scientists go on checking its forecasts against the dim, ancient glow of the sky and the manner in which galaxies lie scattered. Even so, it stays a profoundly powerful thought, that a shaving of one instant may have molded the whole observable universe you dwell within. And here lies the part I find tenderest of them all. Down at the smallest scales, that early universe was never flawlessly smooth. The quantum world hints that faint quiverings were forever there, slight unevennesses in density and in energy, on hand from the earliest conditions. Standing alone, they were unthinkably small. But as the cosmos drew open, those little flickers were pulled up to colossal size, and then gravity handed them their meaning. Wherever matter pooled a touch denser, more matter crept slowly together. Little by little, those faint head starts ballooned into grand structures. Gas gathered close, stars caught and lit, galaxies assembled. Clusters were drawn into still grander patterns. The immense web of the cosmos took its start in these fragile flaws. There lies one of the loveliest threads in all of science, that the largest things we chart today may follow their lineage back to the smallest whispers there could be. As astronomers map out the grand clusters of galaxies, it is held that they are decoding the magnified result of old quantum uncertainty, raised up by gravity over almost the entire long career of the universe. And within those very first moments, matter only narrowly edged out antimatter, the early cosmos having turned out the pair in nearly perfectly matched measure. Let me tell you about a feud that settled everything, ages before any star existed to witness it. Back in the cosmos's earliest instance, matter was born with a twin, and the name of that twin was antimatter. Each time the pair came into contact, they unmade one another utterly, melting into a burst of raw energy. And here is the curious thing I'd like you to cradle softly in your thoughts as you drift off. Had both sides come out exactly even, hardly a trace would have endured. No suns, no seas, no worlds, no chemistry, no you and me. The whole of creation would have dispersed into pure radiation and faded into cold emptiness. Yet the balance shifted by the faintest margin. Why it tilted the way it did is something scientists are still working to unravel. For each enormous crowd of antimatter particles, there appears to have been a hair's breadth more of the ordinary kind, the slightest excess you could picture. And once the two opposing hosts had wiped each other away across numbers beyond counting, that meager remainder turned into every bit of substance that exists. Each galaxy wheeling quietly through the blackness, each drifting wisp of gas, each living cell, traces its existence back to that old, dim lopsidedness. Researchers pursue that riddle in the tiniest arenas within their grasp, watching how nature, under uncommon circumstances, handles matter and its opposite with a hair's difference. The question keeps us humble, since it probes why anything firm survived in the first place. That we are here at all may hang on one of the narrowest triumphs ever achieved. Let me set your mind at ease that antimatter is no teller's fancy. The thing is real, it lends itself to measurement, and we manufacture it deliberately inside high-energy experiments while it also crops up now and again out in nature. Each antiparticle bears a mass identical to its everyday counterpart, only with its electric charge, or some kindred trait, reversed into the opposite. Amid the blistering warmth of the infant cosmos, particles paired with their opposites endlessly flickered into being and blotted one another out. As the heat ebbed, such creation grew scarcer, though the mutual undoing pressed on anywhere opposites crossed paths. Since matter clung to its thin advantage, the antimatter was very nearly scrubbed away. Even now we turn up no sprawling kingdoms made from it, no stars of antimatter, no galaxies of it either. Mere faint quantities still linger within cosmic rays, within radioactive decay, within the wreckage of collisions. That very absence stands as a sort of footprint, the trace of a vast companion that once brimmed throughout the young cosmos and then slipped away so thoroughly that its missing presence grew into one of the profoundest puzzles we hold. Now let me bear you onward, to the instant the universe first allowed light to roam unhindered. Through a long age following the start, the naked nuclei of atoms wandered apart from their electrons inside a luminous haze, much too scorching to unite. Light could scarcely cross any distance, since stray electrons kept batting the photons off course. But the cosmos went on swelling and chilling, until at last the electrons could tuck themselves around the nuclei and remain. We name that mild, settling recombination, although in reality it marked the very first occasion electrons and nuclei bound together. Hydrogen, most abundant of all the elements, slipped into its calm, neutral shape. And all at once, the haze lifted. Around 380,000 years past the beginning, space turned see-through, and the light long imprisoned poured outward. We still glimpse that age-old shine even now, as a dim afterglow steeping the entire sky, the cosmic microwave background. A pair of astronomers, Penzias and Wilson, chanced upon it in 1965 as a hiss they couldn't account for, and it proved to be the most ancient light in existence. With the atoms gone neutral, matter could finally collect under gravity for real, no longer jostled by radiation. A cosmos of penned-in light had turned into a cosmos where structure could start to take shape. Hydrogen, that plainest of atoms, grew into the great raw stuff of all that came after. A single proton paired with a single electron, simple beside the ornate elements within stone and salt water and bone, and still its very simplicity placed it everywhere. Once the chilling set in, it brimmed through space in staggering measure. Gravity gathered it into clouds, and those clouds would someday nurse the earliest stars. Far down in stellar cores, hydrogen nuclei merge and spill out light, and every ordinary star spends a good share of its existence converting hydrogen into helium. Lacking it there would be no slow-burning suns, no warm planets wheeling about them, none of the deeper chemistry that future generations of stars would later concoct. And helium, oddly enough, predates any star. We're inclined to picture elements as products stars fashion, and largely that holds, yet helium owns an older origin. Within the opening few minutes, the whole cosmos ran hot and packed enough to serve as a forge. Protons and neutrons merged into light nuclei, leaving behind a hearty portion of helium and slight traces of further light elements, in what bears the name Big Bang nucleosynthesis. The process wrapped up nearly the moment it started, as the swelling cooled it all. and left a cosmos of chiefly hydrogen, carrying a genuine share of helium. By the time the first stars later kindled, they weren't crafting helium amid some empty barrenness. They were raising it atop a stockpile already set in place. That early helium ranks among our strongest evidence for a hot origin, because the quantity we forecast lines up with what we observe wherever we turn our gaze. For a lengthy span, though, the universe carried no planets, no dust, no starlight whatsoever. It was a broad sweep of hydrogen and helium, cooling as it stretched, bearing the ingredients of every wonder still to come, but not one of those wonders themselves. Gravity was already drawing the marginally denser patches inward, but gradually, ever so gradually. Gas had to assemble and squeeze and warm and tumble together before any star could ignite. This ranks among the notions I find most stirring in all of cosmology. The cosmos did not show up already lovely. It had to fashion its own grandeur. After the light won its freedom, there followed a long, quiet interval we name the cosmic dark ages. Matter lay everywhere, and still nothing glowed. Hydrogen drifted along, and the slight unevenness in its density grew deeper, clouds silently thickening toward the instant fusion might commence. When the earliest stars at last caught fire, they may have been titans, sprung from almost untainted hydrogen and helium, holding scarcely any of the heavier elements that aid gas in shedding its warmth. Those primeval clouds could only cool feebly, and so they crumpled into colossal stars, much vaster than most coming into being today. We name them population 3 stars, and their lifetimes ran short and ferocious, devouring their fuel within a mere few million years, where our sun endures for billions. We have never caught sight of a pristine one head-on, but their fingerprints may lie concealed within the oldest gas and the most venerable surviving stars. And as they perished, those first titans achieved something remarkable, for within their cores, pressure and heat drove nuclei together and set to forging the heavier elements, broadening the universe's slim chemical vocabulary at long last. Let me slow us down here for a moment, because what I want to show you next did not arrive in a single bright instant. It came together patiently, one starry generation passing something along to the next. Some stars, through their long, quiet seasons of inner burning, learned to make carbon and a touch of nitrogen. The heavier ones, the giants, pressed further still and shaped things like silicon and sulfur before their lives ran out. And when those stars at last let go of everything they had built, the clouds that followed were a little richer than the ones that came before. That is the reason, you know, that astronomers will call nearly anything heavier than helium a metal, even when it is plainly nothing of the kind in everyday talk. To them, that word is really a sort of memory, a tally of how many stars have already lived and burned out upstream of us. The cosmos turned chemically interesting only through all of that living and dying. Without those earliest furnaces, space would have stayed too bare, too simple, for any rocky world to find a foothold. So it was the supernova that flung out the seeds of solid worlds. The dying of a massive star, I find, ranks among the most generous events in all of nature. Its core falls inward, while the outer shells are hurled away at speeds that are hard even to hold in the mind, carrying freshly forged elements off into the dark. That blast does not merely break things apart, it enriches. Oxygen and magnesium, silicon and calcium, and so much more go spilling into the clouds between the stars, blending with the older gas already drifting there. And in time, a few of those clouds will sag and fall together into new suns and new families of planets. The very specks of dust that go into making worlds often carry matter that has already passed through one of these endings. So a rocky planet, you see, is not simply gathered out of calm, leftover crumbs. It can be built from the scattered ash of stars that died in catastrophe. Earth's crust, its mountains, the minerals under your feet. All of it belongs to a chain that reaches back through such explosions. Supernovae are terrifying in their scale, and yet they create. They turn the insides of stars into the future stone of worlds. The gold, too, most likely arose from a violence of another kind. For a long while we grasped that the truly heavy, precious elements demanded conditions stranger than ordinary stellar burning, yet exactly where many of them were born stayed a quiet mystery. Then astronomers watched the wreckage left when two neutron stars merge, and at last the proof shone clear. When a pair of these impossibly dense remnants spiral inward and meet, they tear matter free under conditions almost without parallel anywhere. In that flung-out debris, atomic nuclei swallow neutrons in a great hurry, racing to assemble the heaviest elements before all of it settles into something stable. From this come gold and platinum and other rare things. The merger also lights up with a glow we name a kilonova, and that light carries the fingerprints of metals only just made. Think gently on what that means. A ring upon a hand, or a small fleck of gold within a circuit, may hold atoms born when dead stars collided. Something we prize for its quiet beauty here may have begun in one of the most violent embraces the universe can stage. And the carbon, the very stuff of you, was cooked within aging red giants. Carbon sits at the core of life because it bonds so freely, in such flexible and intricate ways. Yet it was not plentiful when things began. One of its great sources is the inside of a star that has swollen, late in its life, into a red giant. Once such a star has burned through most of its hydrogen, its core shifts, and helium starts fusing into carbon by way of a delicate chain of steps. It is believed this calls for a remarkable balance of nuclear physics to work at all. 3 helium nuclei have to find one another amid heat and crushing density, and what comes out of that meeting is carbon. Later, the star can dredge the new material up from its depths and breathe it out on slow winds. Some of that carbon turns to dust. Some drifts into clouds that will one day make new stars. Some, in the end, becomes worlds and air and oceans and living things. The element that strings together the long chains of biology was readied inside stars that were nearing their own endings. Our living chemistry, in other words, has an ancient kitchen up among the stars. Oxygen grew common for a different reason. It became plentiful because the massive stars lived fast and died young. Oxygen ranks among the great elements of the whole cosmos. It fills the rocks, the water, the air, the tissue of your body, and yet how much of it exists leans heavily on those big, hurried stars. They burn hotter and quicker than smaller suns. Deep within them, during the late stages of their burning, nuclear reactions assemble oxygen out of lighter pieces. And because such stars lead short lives, they hand it all back to space quickly, in cosmic terms. Their winds and their explosions enrich the gas nearby with oxygen long before the smaller, slower stars have even finished their patient evolution. This matters more than you might guess for the planets. Oxygen happily pairs with hydrogen and iron, with magnesium and silicon too, helping to fashion both minerals and water. When astronomers study oxygen in faraway galaxies, they are really reading off the pace of stellar birth and death. The oxygen in your next breath did not reach you already as a molecule from those old blasts, but the atoms themselves took shape in stars that burned brilliantly and then ended hard. Iron, now, marks a kind of ending. It is the last fuel of many massive stars. A great star stays alive by balancing gravity against the energy pouring out of fusion. Through most of its life, that outward push holds the star up against its own enormous weight, and as it ages, it works through fuel after fuel in nested shells, building heavier elements down inside its core. But iron is different. Fusing iron returns no useful energy the way the lighter elements do. Rather than holding the star up, iron is a sign its core has come to a dead end. Once enough of it has gathered, the support beneath fails. Gravity wins, and the core caves in with astonishing speed. That collapse can set off a supernova, throwing the outer shells outward while the heart of the star is left as a compact remnant. We know iron well in our tools and our buildings, in our blood and in the cores of planets. But inside a dying giant, it carries something far more dramatic. It is the ash of fusion, the place where one kind of stellar life simply can go no further. For a few weeks, such an explosion can outshine its whole galaxy. When a star tears itself apart at the close, the energy let loose is so vast that one single point of light can rival billions of stars together. For a little while, the dying star may glow brighter than the entire galaxy that holds it. Astronomers can catch these events across staggering distances, which makes them powerful landmarks in the long story of the universe. Some supernovae even brighten and dim in dependable patterns, and that lets us gauge cosmic distances and watch how space itself keeps expanding. In fact, it was exactly this kind of standard candle that, in 1998, led astronomers to a startling discovery: that the swelling of the universe is not slowing, but quietly speeding up, driven by something we now name dark energy. Up close, of course, such a blast would be ruinous. From far off, it is a brilliant signal that something profound has occurred. The shock waves ripple outward through nearby gas, sometimes squeezing clouds and shaping the stars that will form next, and it leaves behind a glowing remnant that lingers for thousands of years. A supernova is not only a final flare, it is an announcement, a delivery of fresh chemistry, and a cosmic beacon, all at the very same time. What remains can be stranger still. A neutron star is a city-sized remnant carrying a star's worth of mass. After certain massive stars explode, their cores fall in upon themselves until ordinary atoms can no longer endure. Protons and electrons are pressed into one another, and what is left is matter ruled almost wholly by neutrons. The result may carry a heavier load than the sun itself, folded into a sphere only about as wide as a large city. That density is nearly impossible to picture. A mere spoonful of such stuff would outweigh whole mountains if it could ever rest here on the Earth. The gravity at its surface is fierce, and the crust, astronomers think, may be tougher than any substance we have ever named. These are not simply dead cinders. They can spin at a furious rate, hold ferocious magnetic fields, and pour out powerful radiation. Their hidden interiors may hold exotic forms of matter that no laboratory could ever recreate. A neutron star is, in a way, an experiment that gravity itself performs, taking the leftover core of a star and squeezing it until matter slips into a realm far past anything we will ever touch. And some of them flash for us, with an almost unbelievable regularity, as they turn. A few neutron stars announce themselves like cosmic lighthouses. From their magnetic poles, they fling out beams of radiation, and should one of those beams happen to sweep over the Earth, our telescopes pick up a pulse. The timing can be extraordinarily exact. Some of these pulsars spin many times within a single second, while others tick along more slowly, and yet their signals can hold steady enough to rival our finest clocks. It was this very steadiness that first told astronomers they were not watching random flickers at all. Let me linger with those whirling remnants a little while longer, you and I, because they have quietly turned into some of the handiest instruments in all of astronomy. A pulsar serves as a tool now, a way to feel out gravity, to probe matter crushed denser than anything we could ever manufacture, and to sense the faint gas adrift among the stars. Listen carefully to its pulse, and it will reveal whether it circles some hidden partner, whether it is plowing through cloud, whether it is slowly leaking away the energy of its own spin. Certain scientists link many such objects together into a sprawling, listening array, hoping to snare gravitational waves so long and so slow that nothing else could expose them. What first reached us as a baffling, repeating tick out of the dark has grown into one of the greatest discoveries we have ever made. A dead star, you see, can declare its presence not through a calm glow, but through a heartbeat steady enough to take the measure of the heavens. Now let me show you the wildest of every neutron star. We name them magnetars, and they bear the fiercest magnetic fields ever detected anywhere. Picture a field 1,000 trillion times mightier than the one nudging a compass needle here on Earth, so intense that the very behavior of matter warps around it. That force can clamp onto the star's crust and squeeze until it fractures, and the moment it breaks, an immense torrent of radiation at the highest energies floods outward. A few of these flares grow so violent that they jostle our instruments and our satellites from clear across our galaxy. The body itself might span no more than a city, yet its reach is colossal, and it is anything but gentle. The thinking goes that a magnetar arrives when one particular flavor of stellar core caves in under conditions that crank its magnetism up to nearly unthinkable heights. Such stars never shine in the calm, unwavering manner of the others. They erupt without warning, as if their own magnetic fields are coiling tighter and then tearing loose. They remind us that gravity does not stand alone in its power to drive the cosmos to extremes. Magnetism, folded into a star that has collapsed, becomes one of the most savage forces in all of nature. But not every star bows out so loudly, and I want to carry you somewhere quieter now. Some merely fade. A star a great deal like our own sun walks a slower, gentler road toward its end. First it swells into a red giant, then it flings its outer layers off into the dark, and what stays behind is a tiny, blazing hot core. That core is a white dwarf. It has shut down the everyday fusion that once kindled it, yet it still clings to the heat of all it used to be, and it cools by slow degrees, glowing only with that hoarded warmth. Inside, gravity crams the material impossibly close, but what props it up is nothing like the pressure of ordinary gas. It is a peculiar quantum pressure, a refusal by nature to be compressed any further. So you can end up with something roughly Earth's size, carrying a mass near the sun's own. Around it, those discarded outer shells may flare into a planetary nebula, settling into soft veils of luminous gas. This counts as a quiet ending only when you set it next to a supernova. It remains a profound change, a star that once warmed worlds turning into a dense and patient ember. And here is something that amazes me each time around. A white dwarf can go on glowing far longer than the whole age of the universe up to now. It consumes no fuel the way a living star does, yet on it shines, pulling its light from heat locked deep in that compact core. Being so small and so dense, it gives up that warmth with painful slowness. The cosmos is simply not ancient enough that even one white dwarf could have chilled the entire way down into the cold, lightless state we name a black dwarf. Each one we can spot is still partway along that long, unhurried descent. That makes them marvelous clocks for the heavens. By reading off their warmth and their dimness, astronomers can put a number on the ages of entire star populations. And far ahead in time, once the brighter stars have all winked out, white dwarfs may rank among the last faint lights left in aging galaxies. They teach us that a star's death is not always quick. Now and then, it is a fading so leisurely that the universe has yet to find time to finish even its very first cases. Let me show you something stranger yet, suspended between the tiniest stars and the biggest planets. We name them brown dwarfs, failed stars that never properly caught fire. They take shape the way stars take shape, out of a cloud of gas folding inward, yet they never amass enough heft to keep genuine hydrogen fusion alive in their cores. A few can fleetingly burn a heavier relative of hydrogen called deuterium, yet they never settle into steady starhood the way our sun managed. They radiate only a feeble warmth left from their birth, dimming bit by bit until they grow terribly hard to spot at all. Their skies can hold clouds and storms and molecules that seem more at home on a giant planet than on a star. Still, they are born like stars, often wandering alone or held in broad, lonely orbits. They blur the tidy lines we once drew. Neither quite planets nor quite stars, they dwell in the borderland between ignition and failure, where nature comes within a breath of lighting a sun and then lets it slide into a long, dim afterlife. The tiniest genuine stars, though, are also the most patient there are. Red dwarfs consume their hydrogen slowly and carefully, cool and dim, sipping at their reserves instead of gulping. Because they spend so frugally, they can outlive a star like the sun many times over. A few may stay lit for trillions of years, far past the age the universe has so far attained, which means not a single red dwarf has yet run through its full span. They are plentiful besides, accounting for a huge fraction of every star in the galaxy, and planets may be common around them, though stellar flares and cramped orbits can leave those worlds as harsher places to live. In the far future, once the larger stars have guttered out, red dwarfs may go on glowing still, the slow-burning hearths of an older and stiller cosmos. Their staying power gently shifts how I think about time. Set beside the lifespans of its smallest stars, the cosmos we know stays remarkably young. And in that distant cold, astronomers suspect the very weave of space will keep stretching, the expansion that turned out to be quietly accelerating back in 1998, sweeping everything toward a dark and frozen far horizon. Now let me carry you home, to our own sun, because it did not rise from pristine gas. It coalesced from a cloud already seasoned by older generations of stars. That cloud carried hydrogen and helium, true, but also heavier elements forged inside suns that had lived and died long before ours came to be. Those ingredients folded into the newborn solar system, passed down to the sun and to the planets, the moons, the asteroids, and the comets alike. We can still trace that inheritance in the chemistry of meteorites and in the elements threaded through the sun itself. So our solar system is not the story's opening line. Think of it instead as a later paragraph within a far more ancient galactic tale. Before our sun ever blazed, other stars had already minted silicon and iron, carbon and oxygen, and a great many other elements besides. A closer look hints that some of the heaviest, gold and yet more iron among them, were forged in supernovae and in the ferocious collision of neutron stars. Their scattered ashes drifted across interstellar space until gravity drew them back together once more. Our daylight pours from a star lifted out of cosmic recycling, holding within it the memory of vanished suns. That same sun took shape inside a spinning disk, and so did we. As that infalling cloud of dust and gas drew tight under its own gravity, its faint spin grew steadily more decisive, and the material flattened into a disk wheeling around the young star. That disk was the cradle of the planets. Close in, where the heat was fierce, metals and rocky minerals could settle out, while lighter ices struggled to survive. Out beyond, in the cold, more fragile, volatile stuff could freeze and collect. Within the disk, grains of dust crashed together and clumped, shattered and clumped over again, until larger bodies took form and swept up everything in their path. The layout of the solar system still remembers that disk. The planets circle within roughly one flat plane because they grew inside that flattened ring. It is a quiet sort of beauty. Order rising up out of collapse, a drifting cloud becoming a turning nursery, and out of that nursery, the sun's entire family of worlds. Those worlds began as next to nothing, as grains of dust finding one another in the dark. The earliest steps toward building a planet were astonishingly tiny, Minute particles in the young disk met, sometimes glancing apart, sometimes clinging together through the faintest of forces. The grains turned into clumps, the clumps into pebbles, then boulders, then bodies big enough that gravity at last began to count. And once gravity took hold, the growth could quicken. The larger bodies pulled in more material, while collisions grew forceful enough that they could reshape or even melt these infant worlds. It was a messy making, hardly a smooth one. Many early objects were torn apart. Others fused together. Some were hurled into strange new orbits or cast out and lost entirely to the dark. Out of all that swirling debris left behind, entire worlds slowly assembled, and it quietly amazes me that the very ground holding you tonight was made this way. Come, and I'll walk you through it. Nothing was planned. There was never a single instant when a mote of dust chose to turn itself into a planet. What there was, instead, was only collecting and colliding and heating, and against the odds, enduring. A world such as this one began as specks so dim you'd never have caught them drifting through the dark ring circling a youthful sun.
Let me bring you to the giant that kept watch over the whole affair.
Jupiter is hardly just another world looping around our star. It is the biggest of them, and its grip has reached across the entire planetary clan. Back in those first days, astronomers suspect Jupiter could have wandered across the disk, shoving little bodies aside and dictating where the remaining material was permitted to pool. It molded the asteroid belt, it leaned on the inner planets while they were forming, and it hurled icy wanderers outward toward distant frontiers. A few models hint that Jupiter alongside Saturn, in concert, stopped the inner region from cramming itself with big rocky worlds. And the work continues. To this day, its gravity can guide a comet or an asteroid, pulling certain ones close and hurling others clean away from the sun. It performs a double duty, both mischief maker and protector, hinging on whatever drifts nearby. Strip it away, and all that surrounds you might have ended up unrecognizable. So Earth's tale is never entirely its own. It bears the marks of that colossal companion out in the distant dark. Your homeworld was not laid down softly. Across the busy young inner region, rocky bodies looped the sun on routes that constantly intersected, and they smashed together again and again, welding into bigger things by way of collisions that unleashed staggering heat. Here and there, Earth flowed molten.
The dense matter dropped,
Iron drifting toward the middle to build the core, while the lighter silicate rock rose into mantle and crust. Every strike rewrote the swelling world, its mass, its makeup, the manner of its turning, the heat locked inside. Certain blows brought fresh material, while others ripped debris back out into the void. The thinking is that this dragged on through many tens of millions of years, until what was left afterwards still burned, still churned, still kept building. This explains the layers Earth carries, why it held on to its inner fire, why that early surface would strike you as so alien. The hushed field under your soles is the cooled flooring of an old construction site, raised through collision. I believe one of those crashes handed you the moon. The preferred notion holds that something roughly Mars-sized, named Theia in some tellings, struck the young Earth toward the close of its assembly. The hit was so brutal, it flung enormous quantities of matter into orbit, and out of that ring of wreckage, the moon gradually pulled itself together. This clears up a few mysteries, such as why our companion runs so large relative to its world, and why certain chemical signatures within lunar rock so closely mirror Earth's mantle. The impact would have refashioned our planet, pouring in heat and altering its spin. And the moon paid us back, holding Earth's tilt steady and calling the tides into existence. A disaster turned into one cause of the rhythms your world still keeps.
That pale circle riding above you may be the enduring offspring of something dreadfully violent.
And as for the water, it came from more than a single origin. Part of it may have been worked into the very material that assembled the planet, locked away within minerals, or ferried in by moist, rocky bodies. More probably came later, brought by asteroids loaded with water-bearing compounds. Comets were the early frontrunner, yet a nearer inspection implies many bear water whose isotopic signature fits ours less tidily than particular asteroid families do. In all likelihood, the answer is a mixture, accumulated over a great span. Water might have traveled inside minerals throughout Earth's formation, then been exhaled by volcanoes, then replenished through later impacts. This counts because water sculpted the surface, nourished the air, established the climate, and unlocked the way to life. That glass you may sip from tonight is nothing local in the least. It is part of a long saga of minerals and impacts, and a planet reshaping itself. There are stones holding the memory of every bit of this. A meteorite can resemble any ordinary rock you'd walk past without noticing, and yet some predate Earth. A handful contain primitive material born in the early disk before the planets were complete. Minute mineral grains and metal flecks and chemical patterns logging the solar system's earliest conditions.
A few even bear pre-solar grains, formed around other stars before our sun came to be, that endured the long plunge into the cloud that birthed us and got trapped within small bodies that never melted through. Whenever one of these arrives, scientists obtain a sample from an era no spacecraft could ever travel to. Studying their isotopes in minerals, researchers reassemble the temperatures and timelines of those first chapters. Cradled in your palm, such a stone may carry matter older than the sun, dating from before Earth bore any name. Comets hold onto frozen diaries of their own. Distant from the sun's heat, icy bodies preserved materials too fragile to endure in warmer locales. Blends of ice and dust, and organic molecules and rocky grains, kept for billions of years within the chilled outer reservoirs. As one drifts inward, sunlight rouses its surface and gas pours off, hauling dust with it, and that becomes the luminous coma and tail that make a comet so enchanting to behold. Yet the beauty is merely a fraction of the matter. Their composition murmurs of the early disk and the frigid zones where the ices first gathered. Probes have cruised beside them, sampled their gases, captured their dark faces in close detail. They are no plain, dirty snowballs. They are layered mementos of the sun's early days, guarding delicate chemistry that whispers how worlds came into being. The asteroid belt sits between Mars and Jupiter, and I ought to tell you it is not the debris of a single broken planet, no matter how frequently that tale gets repeated. Its total mass is far too meager, and its bodies differ too widely in composition to be the shards of one world. Rather, it is a place where a planet attempted to form and never fully succeeded. Jupiter's gravity drove much of that, agitating orbits and barring the material from gathering into one steady world. Crashes kept occurring, though they leaned toward shattering things instead of constructing them. Nowadays, the belt carries objects of every size, from the dwarf planet Ceres on down to little fragments and loose rubble piles, some metallic, some rocky, some darkened with carbon. It is a museum of construction left incomplete, and that very unfinished character is precisely what makes it precious. Now let me take you well beyond Neptune, out to an immense ring of icy bodies floating along the cold rim of the system. Their courses are anything but random. Through billions of years, Neptune's gravity has set many of them in order. Some sit locked within orbital resonances, looping the sun in rhythm with Neptune's own circuit, and Pluto is the famed one snared in such a dance. These resonances can guard a body against close encounters, while still exposing Neptune's silent hand. Astronomers suspect the planet may have wandered outward in the distant past, flinging icy bodies into new orbits and establishing the arrangement we encounter now. So the Kuiper Belt is no mere faraway attic of cast-offs. It is a place inscribed throughout by the long memory of gravity. Should you let your thoughts wander still further onward, beyond all this unhurried making, the universe itself is bound somewhere. A great many astronomers hold that it closes not in flame, but in cold, a drawn-out big freeze, a heat death, the galaxies receding ever farther into the dark until the final light dies and the warmth dwindles down toward nothing. But that lies unimaginably distant from tonight, and for now there remains the tender labor of worlds taking form, and the stillness between the stars, and you, at rest here, cradled by a planet that was raised grain upon grain. Let me carry you out beyond Neptune now, to where sunlight has thinned almost to nothing, and everything drifts so slowly that one orbit would stretch across a whole lifetime. When researchers trace the soft, looping paths of the little frozen objects scattered out here, they can wind the clock backward and picture how the giant ones rearranged themselves so long ago. Neptune lies tremendously far from us, and still its hushed pull keeps signing its name over this frozen rim. I'd like you to meet Pluto, though not as the lonely little curiosity you might recall. Through nearly all of the previous century, that was the picture, a single odd planet wandering on its own. Then, little by little, telescopes kept turning up more chilled bodies out past Neptune, and at last, Pluto's real neighborhood swam into view. It sits inside the Kuiper Belt, a wide ring of frosted worlds, shattered fragments, and dwarf planets. A few carry tiny moons of their own. A few show ruddy complexions, tinted by sluggish and knotted chemistry. A few ride along tilted or drawn-out trajectories, soft traces of some unsettled beginning. Pluto is still astonishing, truly. When a probe at last slipped past it, the craft found peaks sculpted from frozen water, level fields of nitrogen ice, and clues that the ground there is somehow restless even now. Yet it stands no longer by itself in our thoughts. It belongs to an entire population, the kind that softly redrew where we trace the edges of our planetary realm. Stripping away its planet title was never a forfeit of awe. To me it reads as a welcome, a gateway swinging wide onto a sweeping frontier of small, remote worlds. Float onward with me, well past even that ring, and let me reveal something no eyes have ever truly caught. Astronomers suspect that an immense round shell of frozen bodies enfolds the sun, the Oort cloud, cradling old comets within the far-off dark. Nobody has ever glimpsed it head-on. The pieces inside are simply too tiny, too frigid, and flung across too much vacancy to catch much light at all. Our only hint comes indirectly, from those long-period comets dropping inward out of every angle at once, as though their voyages began inside a huge bubble wrapped around us in all directions. Such comets probably took shape nearer the giant planets, and gravity then slung them far outward in the distant past. Out there, they glide along gigantic arcs that may need millions of years to close. Now and then a star sliding by, or the slow tug of the galaxy itself, jostles one loose and aims it back toward the sun. Should that cloud genuinely be there, it forms the sun's most remote household, less a barrier ringing the edge than a dim, distant recollection, safekeeping frozen mementos from our origin. Not every world, though, answers to a star. Certain ones roam the galaxy entirely solitary, with no sun to claim as theirs. Imagine a planet adrift in the dark between stars, never bathed in any dawn, never brushed by the seasons we know. Plenty of these were likely born around stars and afterward flung loose amid gravitational turmoil, especially during those crowded early eras when fledgling systems shoved one another about. Others may have gathered straight out of collapsing gas, closer to small failed stars than to genuine planets. Lacking any star nearby, their outer layers would be savagely cold. And yet, that hardly leaves them barren or lifeless. A dense atmosphere might seal internal warmth inside, An icy shell could hide a buried liquid sea, held unfrozen from beneath by radioactive decay or the lingering trace of ancient tides. A few may even drag moons along with them, little systems sailing as one through the dark. We catch them through gravitational microlensing, that fleeting instant when a roaming world bends the rays of a faraway star behind it. They remind me that no world needs a sunrise to carry a story. And if you ever sense just how hollow that gulf between the stars really is, recall that the galaxy holds emptier stretches yet. Enormous cosmic voids like the Boötes void, a span so huge and so nearly barren that a lone wanderer within could journey across it for ages and turn up almost nothing whatsoever. Other worlds, by contrast, claim not one sun, but a pair. For ages, planets lit by twin stars existed only inside our tails. Then real examples surfaced, looping about binary stars, showing nature can raise stable worlds even where we'd once supposed only mayhem reigned. At times, a single lone planet circles both stars together, drawing a broad arc around their shared midpoint. Stand upon such a world, and the heavens would unfold in ways that would unsettle you. A day's length might drift as the paired suns eclipse each other and swap positions. Shadows would not fall the way they fall here. The seasons might answer not merely to the planet's tilt, but to the unhurried waltz of the stars themselves. These worlds prove hard to spot, since the doubled glow muddies the signal, though several stand confirmed by now. Nearer yet to their star, certain planets wrap up a full year in mere days. The earliest worlds spotted circling sun-like stars left astronomers reeling, since nothing in our own backyard looked like them. These hot Jupiters, giants as large as our biggest planet, tear around in cramped, blistering loops. Their outer air takes a battering from radiation, baked to extremes, now and then ballooned into huge, swollen shrouds. Many sit tidally locked, one cheek in unending blaze, the other in unbroken night, with savage winds ripping between. The genuine riddle is how they arrived, since such giants supposedly assemble far out where ice runs abundant, so they must have wandered inward or been jostled by gravity. Closer still, and the rock itself melts to liquid. On the daytime face of these lava worlds, it climbs hot enough to soften stone, and in place of water, there may be radiant seas of liquefied silicate with swells of mineral that would harden into cliffs back home on Earth. The air, if any survives, might be vaporized rock and sodium, drifting toward chillier ground to fall as an odd mineral rain. One celebrated blue world holds winds so brutal that calling its weather rain feels much too soft. Its tint probably traces back to minute silicate grains riding high above, the raw makings of glass, hurled sideways through a thundering sky. Seen from far off, it looks lovely and nearly inviting, which only shows how looks mislead out here. And let me send you off with the tenderest of them all. A few worlds tuck whole oceans beneath shells of ice, warmed from somewhere within. Within our own system, Europa, together with Enceladus, already murmur of this, their hidden seas kept liquid by the kneading grip of gravity. A frozen crust can guard that water, holding it secure and steady. Around distant stars, such still seas might lie everywhere, biding their time in the dark. Let me linger here beside you in the hush, and tilt our minds toward how peculiar far-off worlds could turn out to be. Beyond our sky, biology stops being a closed chapter and opens wide again. A few of these remote places whisper that living things may not always require a star shining down on bare ground. Life could just as readily wake within seas locked under crusts of ice or stone, nowhere near the heat of any sun. And those worlds themselves need not be built from the same materials that built us. Imagine a star that holds more carbon than oxygen within its body. The scraps left over to clump into planets out there would stray from the blueprint that formed the earth under your feet. Where silicate stone might have ruled, carbon-based compounds could instead step forward. Press that carbon firmly enough, far down inside a dense and rocky body, and a portion might harden into diamond. And yet a place like that would shine as no gem resting on velvet. Think instead of ground that lies dark, blistering, and crushed flat under a savage sort of geology, while far underneath, unreachable veins of crystal could rest concealed in shadow. They stay merely theoretical sketches, not snapshots mailed from any place we recognize, though the logic holds firm, because what a planet grows into hangs on the ingredients it was given the moment it formed. This world of ours brims with oxygen bound up inside stone. Out beyond, a planet's core might be arranged around carbon's curious talent for assuming countless shapes, leaving its inner life unlike anything we would call ordinary. Now let me reveal for you a sort of world our own planetary family simply has none of. Somewhere between how big the Earth is and how big Neptune is, our corner holds a gap, a rung gone missing from the ladder. The larger of these often earn the name super-Earths from astronomers, though to me the label rings slightly off. It guarantees nothing about ease or mercy. All it tells you is that they outmass our planet, while remaining smaller than those frozen giants orbiting farther out. A few might be solid stone beneath your step. Others could be draped in heavy skies, harbor deep waters, or lie buried under thick veils of gas. The gravity there might bear down far more fiercely than the soft tug you sense at this very moment, recasting how peaks climb, how air holds fast, how the surface itself trembles and scorches. Since such bodies appear so frequently around distant suns, their hushed absence in our neighborhood is one of the small riddles that keeps researchers leaning in. To study them is to learn how planets balloon, how an atmosphere gets kept or torn away, and how raw size can guide a world's entire fate. Maybe, somewhere in their ranks, lie planets with calm seasons, churning interiors, and long, unbroken pasts. The galaxy may have strewn Earth-like ingredients over a scale grander than the one we know. A second missing relative waits as well. One of the milder surprises out of the sweeping planet surveys is how plentiful the worlds are that perch just over Earth and just under Neptune, those we name mini-Neptunes. They may bear rocky or icy centers swaddled in thick cowls of hydrogen and helium, with clouds and chemistries we hold nothing close by to set them against. Our own arrangement hands us small, stony bodies near the warmth and towering giants out in the cold, yet nothing occupies this in-between. That very gap makes them deserving of our notice. They could be a commonplace outcome of world building that our system somehow bypassed or silently shed in its turbulent early days. A handful of them crowd close to their suns, where punishing radiation gradually strips their atmospheres bare. Others may cradle those gassy coverings across billions of years. Picturing them sharply is difficult, since no near neighbor waits for a spacecraft to drop by and weigh it. Every one we turn up offers the same gentle nudge. This little corner of ours is no master plan for everything else. It stands as one design among countless others. And here is a tender thing I would have you keep as you drift away. We can sample the air of these worlds without ever drawing near them. As a planet slides across the disk of its star, it dims that glow by the slightest trace, and that small shadow betrays the planet's size and the curve of its journey. But a finer secret nestles within the light itself. A thread of starlight first slips through the planet's own air on its road to us, and the gases waiting there sip up certain colors. Fan that light into its rainbow, and astronomers can hunt down the signatures of carbon dioxide, water vapor, sodium, or methane. A distant world turns into a shadow bearing a chemistry we can decipher. The planet may sit far too remote to appear as more than a speck, yet its air leaves readable traces inscribed across the void dividing the stars. The labor is grueling, because suns blaze fierce and planets are minute against them. But our latest telescopes keep growing keener at the task. Through these faint, breath-soft shifts in the light, we begin to wonder out loud what foreign skies might hold, and whether any among them might tilt toward being a home. Those same steady instruments that decode these atmospheres, with the James Webb Space Telescope foremost among them, have also gazed into the deep past and turned up startlingly luminous, early galaxies shining where we braced for nothing but darkness. Let me pull back now and let you sense the vastness of the place we call home. The Milky Way of ours cradles hundreds of billions of stars, so very many that plain counting loses its grip. The sun stands as merely one within that colossal throng, sprinkled across a flattened disk, a bulging core, and a dim, encircling halo. Some stars flare furious and blue and perish young. Others run small and red and may shine on for spans of time nearly past imagining. Plenty never arrive at our eyes whatsoever, shrouded by dust or distance or simple faintness. From the spot where you lie, the Milky Way reveals itself as a faint stream spilling across the dark, because we peer sidelong through its packed plane from somewhere within. We cannot stroll outside and capture our own dwelling from beyond its bounds. So instead, its chart is assembled from star counts, the slow flow of gas, the shimmer of infrared, and the murmur of radio. What surfaces is a sweeping spiral holding everything we have ever come to know. Each constellation you could name belongs to this single, nearby town of stars. The night is not some chance scattering. It is the vista seen from within a galaxy. And that luminous spiral is merely the portion within our sight. Folded around all those stars and clouds lies a far broader halo of unseen mass, betrayed only by the way its gravity pulls. Stars circling the galaxy's rim sweep around too swiftly for the visible matter to rein them in, and the little dwarf galaxies wheeling about us feel the draw of something wider yet. That halo of dark matter may stretch far past the radiant disk, a tremendous envelope of gravity surrounding us. It throws off no light, intercepts none, and appears to make no ordinary atoms so far as we can presently judge. Even so, it governs how the galaxy keeps itself bound and how it took shape. Strip away that hidden scaffolding, and the Milky Way's form would grow hard to explain. We dwell inside a glowing disk, nested within a sprawling, unseen architecture. Those stars are the only share we are permitted to behold. The unseen halo may be silently keeping it all in place. At the deepest core of our galaxy crouches something darker yet. There a body so packed and weighty holds sway that the stars nearby tear around it at dizzying speeds. Astronomers traced those stellar orbits with patience, season upon season, and saw them loop about a thing beyond their sight, cramming millions of suns into a minuscule pocket of space. Sagittarius A star is what we call it. It runs far quieter than the blinding black holes that ignite quasars, yet it remains the steadying gravitational heart that holds the galactic core, encircled by jammed stars, drifting gas, snarled magnetic fields, and unsettled radiation. Every so often, a wisp of matter spills inward and flares, granting a fleeting peek at the physics beside the edge of no return. From how those stars move, and from one celebrated star that swings in remarkably tight, the figure settles near 4 million suns compressed inside a span tinier than the whole of our own planetary system. That floors us. Yet it stays modest against the behemoths in other galaxies whose mass climbs into the billions of suns. So our own Sagittarius A star turns out to be at once ferocious and curiously held back, presiding over the center without devouring hard enough to flare bright. Its stillness lets us examine a supermassive black hole right here in our own pocket of the cosmos, near enough to read details that more distant galaxies will never give up. Rest now, and let the slow wheeling of all that gravity carry you softly downward. Let me turn your gaze gently now toward the heart of our galaxy, where motion outpaces anything that feels possible. Whatever stars sit nearest the Milky Way's core are held in a grip so fierce it would seem unthinkable out here in our calmer corner. A few of them tear past at thousands of kilometers every second while looping around the dark middle of it all. And here is the beautiful thing. Those frenzied tracks amount to more than a show. Through years of patiently noting where these stars rest, astronomers deduced that a staggering quantity of matter must lie crammed into a space almost vanishingly small at the middle. The stars turn into tiny instruments, sketching out an unseen tug. One of them sweeps near enough that its trajectory bends just barely, exactly as Einstein's general relativity predicts space and time ought to warp beside such an object. Picture a star that no one built, dropped by nature alone into precisely the orbit that will murmur the secret of a concealed mass. Around that core, the stars become messengers, and the way they move is the message delivered to us. Now let me carry you back home, to our own unhurried circuit. Earth, as you know, rounds the sun a single time each year. Yet the sun is itself voyaging around the galactic center, and that vastly bigger journey runs to something close to 225 million of our years. Folks will sometimes name one such lap a galactic year. From the moment our solar system first assembled, it has completed barely 20 of them. When we last drifted through this very segment of the galaxy, Earth was nearly impossible to recognize, with its land masses laid out differently, its climates and its creatures a whole other world. And this route is no neat loop. The sun rides along with the spinning disk while softly rising and dipping across the galactic plane, gliding through always shifting fields of gas and dust and fellow stars. The whole of our history runs too brief to sense any of it, yet it never rests. We count out our small days by the climbing sun, while the entirety of our planetary family rides across the Milky Way along a clock that overshadows biology and every empire we have ever built. I ought to mention as well that our galaxy has feasted before. Within it, the Milky Way holds the marks of ancient meals. Far out in the halo wrapped around us, astronomers spot stars wandering in streams and clusters that plainly fail to travel with the main disk. Their chemistry, together with the orbits they hold, hints that they once belonged to lesser galaxies, ripped apart ages ago by the slow hands of gravity. A single, enormous merger deep in our past, decoded from how those stars travel, appears to have spilled, billions of years back, a huge throng of newcomers into that outer halo. Encounters of that kind helped shape the Milky Way into the home we occupy. Nothing about it resembled a monster gulping stars one after another. It was a slow coming apart, one smaller galaxy surrendering its very form and melting into a bigger one. Which is to say, our galaxy is, partly, stitched together from outsiders. A few of the stars overhead may never have come into being here whatsoever. They might be immigrants out of worlds now vanished, threaded quietly into the night above you. Those dim ribbons go by the name stellar streams, and they keep the memory of galaxies we devoured. Whenever a dwarf galaxy or a star cluster spirals inward, tidal forces draw it out into a long filament of stars. A stream like that can coil around the galaxy as a faint track, clinging to the orbit of whatever produced it. Spotting them is difficult, with their stars sprinkled so sparsely across the dark, though modern surveys have turned up plenty. Every one stands as a clue to something now lost. By following a stream's course, scientists can sense out the gravitational form of the Milky Way, even how its dark matter is spread. The streams, then, serve as both fossils and rulers together. They flag where small systems came apart, and they help lay bare the unseen mass through which these ribbons drift. To you, the sky may seem fixed and serene, but tucked into it lie the remnants of old gravitational encounters. A stellar stream is galactic history penned by hand in stars, and there is a single neighbor drawing nearer even as we speak. Most galaxies far off are being carried away from us through the cosmos expanding, but the closer ones can be governed instead by gravity nearby. Andromeda, the most magnificent spiral within our modest local group, is one of those. Across the void separating us, it is gliding toward the Milky Way. Beneath a genuinely dark sky, it appears only as a dim smudge, and yet it cradles roughly 1 trillion stars and reaches across a colossal expanse. Its motion makes plain that these two giant galaxies are bound together and steadily slipping nearer. Please do not read this as any alarm. The timescale runs to billions of years. Even so, I find it marvelous that the sky carries another spiral not merely drifting through. It is part of our distant future. Brief though our lifetimes are, galaxies keep far deeper clocks, and Andromeda's soft glow is at once a nearby island full of stars and the first whisper of a transformation still ahead. The two are thought to converge in something like 4 to 5 billion years. One day, our galaxy and Andromeda are destined to fuse into one. In that remote future, our group's two biggest galaxies are predicted to unite, gradually, across billions of years, while gravity drags them through pass upon pass. Their spiral arms will buckle and stretch and finally blur into something fresh. For all of that scale, the stars themselves are not likely to hit one another, since the gaps dividing them are far too broad. The real drama unfolds within gravity, reshuffling orbits and churning immense clouds of gas. Wherever that gas gets compressed, new stars may ignite. The sun, should it still burn in its old age, might be hurled onto some fresh path far removed from the one it now follows. A merger of this sort reminds me that galaxies are by no means permanent sculptures. They are restless creations, molded by whoever they encounter. That familiar shape of the Milky Way is merely time on loan. Someday our home and its grand neighbor may settle into one single, larger whole. People are still startled that galaxies in collision almost never smash their stars into each other. A pair of galaxies can pass entirely through one another, each bearing hundreds of billions of suns, and hardly any of them will make contact. Scale is the reason. Stars are immense, but the void between them is far more immense. Were the stars grains of sand, the distances parting them would be vast past all imagining. Throughout such an encounter, gravity reworks everything. Orbits drift, spiral arms draw out long, gas clouds crash together and thicken, and star formation can blaze in dazzling patches. Still, the stars themselves chiefly slide quietly past each other through all that open darkness. That is what renders a galaxy collision both violent and oddly spacious. Entire galaxies can be remade while their individual stars pass through untouched. To a world circling any of those suns, the sky would simply brighten slowly, painted across the ages with new arrangements of light. The collision is genuine, and yet it amounts to a gravitational dance far more than a crowded smash-up. Not every galaxy, by the way, wears elegant arms. Some are immense and smooth and settled, with their stars going off in every direction rather than coasting along a thin, turning disk. These are known as elliptical galaxies, and the largest among them are genuine giants. They lean toward holding older stars and fairly little cold gas next to the bustling spirals. Because fresh stars require cold gas to take shape, a great many ellipticals glow with the warm hues of aging suns instead of the blue blaze of new, massive ones. Quite a few of them probably arose from mergers, where spirals shed their tidy disks and eased into wider, puffier shapes. Down in the cores of the biggest ellipticals, the supermassive black holes can be downright staggering, and these galaxies frequently sit enthroned at the center of entire clusters, encircled by lesser companions. An elliptical may seem so plain, just a gentle ball of light. Yet inside it rests the blended tale of many galaxies that went before. It bears recalling, too, that the heavier stuff our worlds are built from, the iron deep in a planet's core, the gold in its crust, was forged in dying supernovae and in neutron stars colliding, then flung out to be drawn together once more. A spiral galaxy ranks among the universe's most recognizable forms, yet its beauty rests on forces we can never fully see. Let me keep your eyes on those luminous spiral arms a moment more, since they hide more than they reveal. True, they brim with stars, with wandering gas and the finest dust, but the manner in which this whole galaxy turns whispers to me that far more is present than any light can ever show you. The thinking among astronomers is that an immense halo made of dark matter cloaks the disk completely, soundless and out of view. Strip away that buried weight, and the stars far out near the rim would refuse to circle the way our measurements catch them circling. As for the spiral form itself, the very feature that steals our breath, it is softer than any rigid pinwheel. People believe it travels rather like a wave instead, a rising tide of density sweeping along the disk, squeezing the gas close until fresh stars catch fire. Those newborn, blazing, youthful suns set the waves' crests glowing, and that is how the arms blaze out for us to see. Whatever you and I marvel at within a telescope picture is merely the shining skin of something far more profound. This galaxy rotates, though never the way a plain wheel turns. Picture a huge, spinning platter, guided by matter our eyes can catch alongside mass they never will, partnered together within the darkness. Now let me bring forward the small ones, since the cosmos rises from the humble every bit as much as from the magnificent. A dwarf galaxy carries far fewer stars than a giant such as our Milky Way, and yet it counts for more than its modest scale would hint. Plenty of them, so astronomers suspect, took shape extremely early within tiny halos made of dark matter, and a handful still hold ancient stars, cradling whispers out of the young universe. While the long ages rolled by, bigger galaxies stretched out and pulled these little neighbors in. Their stars scattered far and wide across dim halos. Their gas was given up to nourish fresh generations of stars. Their dark matter slipped quietly into something larger. And so, the mightiest galaxies are, partly, sown from countless lowly origins. A few dwarfs endure even today, wheeling around their bigger hosts and sensing the slow pull of the tides. To you they might seem dim, yet they are treasured by anyone who studies them, since their faintness leaves them sensitive to every nudge and strain, the blasts from bursting supernovae, the gradual draining of gas, the gentle hand of dark matter. They remind me that nothing builds the universe through spectacle by itself. The little ones lend a hand in sketching the design of the large. Let me steer your gaze towards something savage and distant now. At first glance, a quasar resembles one dazzling pinpoint, nearly a star, and yet its real core is a supermassive black hole seated at a galaxy's center, swallowing whatever drifts close. While gas winds its way in, it pools into a searing disk, and friction, brutal pressure, and snarled magnetic fields warm that disk until radiation spills from it in dizzying quantities. No light leaves the black hole out of its own rim, though the matter falling toward it can flare as among the most radiant things across all the universe. Since we typically spot quasars at staggering ranges, what we truly witness is how they looked back when the cosmos was young, an era when mighty black holes ballooned swiftly and galaxies were still settling into shape. A number of them blast out powerful jets, flinging energy well past the galaxies that contain them. The thing that amazes me the most is how efficient it all is. A volume no larger than the span of our solar system can outglow a whole galaxy, since the gravity close to a black hole converts plunging matter into light with might that nearly defies belief. The wildest quasars outshine galaxies by the thousands together, and their radiance can stretch across almost the entire observable universe and still find our instruments. Seen through a modest telescope, they pose as stars, yet they are active galactic nuclei, burning within the cores of faraway galaxies, fed by matter streaming into supermassive black holes at staggering rates. Among the most extreme of them, the brilliance overtakes thousands of plain galaxies put together. And here is a wonderful thing concerning quasars. We are able to hold them up like lanterns behind the universe. While their light makes its way to us, it filters through gas clouds along its path, and those clouds press their fingerprints onto it, telling us what matter consists of and where it sits throughout cosmic history. So a quasar is at once a subject to examine and an instrument for examining all that lies between it and ourselves. Its brilliance carries a tale of hunger, of gravity, of galaxies still coming of age. A minute core grows into a lamp luminous enough to brighten the far-off past. It calls to my mind, a little, the cosmic microwave background, that faint afterglow Penzias and Wilson chanced upon in 1965, the most ancient light in existence, still drifting softly over us out of the early universe. Black holes themselves swell by feeding, and the meal is seldom neat. A black hole adds mass whenever matter slides past its event horizon, though the route inward is rarely straight. Gas might coil into a disk, heating as it gives up its energy. Dust ends up hauled inward once collisions and turbulence rob it of whatever kept it in orbit. Should a star stray too near, it can be ripped open by tidal forces, its torn matter trailing around the black hole in a brilliant flare. And within the packed cores of galaxies, black holes can swell by fusing with one another. The feeding arrives in fits and starts. Lengthy spells of calm get shattered by abrupt bursts whenever fresh material shows up. Certain black holes rest nearly unseen because next to nothing is dropping in. Others erupt into dazzling engines as they gorge. But growing is more than swallowing, you understand. Before matter slips away, it can cast off radiation, drive mighty winds, and mold the very galaxy surrounding it. I want you to dwell on the notion of the edge itself, the spot from which nothing comes back. A black hole's boundary is no wall you might plant your feet upon. It is a point of no return threaded into space-time. A breath outside it, getting away remains possible provided you race fast enough along the right heading. A breath inside it, every route you might pick bends only further in. Even light, the quickest thing in existence, cannot scramble back out, and that explains why the edge appears black. This horizon takes its meaning not from any surface, but from cause and effect. It parts the events that can still fire a signal outward to the rest of the universe from those that never can again. For anyone slipping across it, inside a truly colossal black hole, there might be no abrupt flash, no barricade, nothing to mark the instant. Yet from that moment forward, turning around would be as hopeless as journeying back into yesterday. That thought strikes me as unsettling and beautiful all at once. A black hole is not simply a thing of great density. It is a region where getting away merely ceases to belong to any future. And yet, oddly, these very same captors of light can fling matter clear across the gulf between galaxies. Certain feeding black holes accomplish far more than swallowing. They release thin beams of particles and radiation that reach well past their home galaxy. The thinking goes that these jets spring from magnetic fields wound taut by whirling accretion disks and the rotation of the black hole itself. matter close to the center gets gathered and hurled outward at velocities near that of light. The jets drill through the gas around them, swell vast bubbles, and dump energy into entire clusters of galaxies. To radio telescopes, they show up as colossal forms, reaching across spans wider than the visible galaxy that birthed them. This feedback can settle whether gas ever chills enough to build new stars, which turns black holes into silent architects of galaxies. The paradox lingers with me. A thing renowned for trapping light can likewise raise some of the broadest visible outflows across the cosmos. There remains one final secret to pass along before we drift onward. Black holes seem like perfect cages, and yet quantum physics hands them a slight, fragile leak. During the 1970s, Stephen Hawking demonstrated that a black hole's edge is not utterly silent. Quantum fields close to that boundary can emit a faint glow, what we have come to call Hawking radiation. For large black holes, that glow is hopelessly weak, cooler even than the background surrounding them, so they soak up more than they hand back. But in theory, should the universe last long enough and turn cold enough, a black hole can gradually dwindle. The tinier it grows, the hotter it gets, and the swifter it fades. This is hardly a rapid vanishing, mind you. Stellar and supermassive black holes would persist across stretches so vast that the universe's present age feels like a single blink alongside them. Even so, the notion is profound. Even the darkest things may not last forever. Gravity, quantum theory, and time, braided together, may hand a black hole its final ending. And then come gravitational waves, ripples coursing through the fabric of space-time itself. Whenever great masses speed up in violent fashion, they can disturb the very weave of space and time, and those tremors stream outward at light's own pace, bearing news of events that might shed barely any ordinary glow at all. Let me hold your attention on something almost too small to imagine. By the time one of these ripples in space-time arrives where we are, it has dwindled to nearly nothing. As it drifts through a detector, it elongates and compresses the instrument by an amount narrower than one proton's width. And even so, that whisper of a change suffices to reveal some of the fiercest moments our cosmos has ever lived through. We catch them using long arms of laser light, machines that gauge separation with a precision that almost defies belief. What gets recorded is not a sound traveling across the void, but a faint figure we can convert into a note that climbs slowly. Folded inside that note lie the masses, the spins, the distances of whatever lay out there. To me, it feels like a wholly different way of reading the sky. For ages, we could only study the heavens by sight. Now, quietly, we get to sense the universe shivering as it sweeps through our little world. The first time we genuinely listened, what reached us was two black holes plunging into one another, and it bore out something Einstein had pictured ages earlier. Across 100 years, general relativity had whispered that wherever gravity churns violently, ripples ought to roll outward through space-time itself. The mathematics carried a real beauty. The signal looked all but impossible to ever register. Then the detectors stationed on our planet caught a short rising chirp, two black holes coiling ever tighter around each other. Its shape lined up with the theory at an accuracy that still leaves me amazed. Inside a sliver of 1 second, those two bodies spilled a staggering quantity of energy outward as gravitational waves, and afterward they had become one, a single larger black hole remaining. No telescope ever watched it shine in ordinary light. We uncovered it solely by sensing the geometry of space flex, right here, within a thing human hands had assembled. And that carried more weight than a clever feat of engineering. It demonstrated that black holes truly can merge, that space-time truly can bear waves, and that gravity itself can serve as a way of studying the cosmos. The signal had been born in a crash that took place before our kind walked the Earth. It traversed the dark, unfathomable gulf and reached us, finally, as the slightest tremor inside a machine. Now let me steer your gaze toward light and how weighty things can bend it. Gravity does more than tug at planets and stars. It also remakes the road along which light moves. When the glow from a remote object slips close to a hefty galaxy or a sprawling cluster of them, its course can bow gently as it travels to us. That foreground weight acts like a lens nature shaped on its own, curving the background image and at times making it brighter. You might catch arcs or rings or that identical far-off galaxy showing up more than once within the same stretch of sky. None of it is a trick played by glass or mirror. It is the form of space-time calmly revealing itself. Astronomers rely on this bending to examine things far too dim to spot otherwise, and to weigh the hidden, including dark matter, which emits no light of its own to give it away. A cosmic lens can take a plain, forgettable scrap of sky and convert it into a deep window. The universe, in a way, helps us peer back at the universe. Gravity turns into a telescope, one nobody had to construct, lifted instead by the sheer mass of galaxies. That very bending lets us study galaxies tucked away behind other galaxies. Now and then, a heavy foreground body aligns almost flawlessly with something far more remote lying past it. Instead of devouring that background galaxy from sight, the nearer gravity wraps that light around the blockage and steers it softly our way. What reaches us might be a long, elongated smear, or at times, a ring that seals into a nearly perfect circle. So we end up able to study galaxies that would ordinarily be too dim, too tiny, or simply too distant for us to perceive at all. This lensing can raise young galaxies out of far earlier cosmic eras and let us inspect their structure in a detail we could never otherwise reach. It also lets us sketch maps of unseen mass, because how strongly the light bends rests on all the gravity present, not merely the stars that happen to glow. In some of our deepest images, those faintest curving streaks rank among the most precious things within the frame. They are magnified messages passed to us from beyond a cosmic wall. The universe does not only conceal things from us. Given just the right alignment, it folds the light around the barrier and grants us a glimpse of what had been waiting on the other side. That carries me to something we have never once watched glowing. No telescope has ever glimpsed dark matter giving off any glow. As far as we can tell, it neither drinks in light, nor flings it back, nor releases a trace of its own in any fashion we recognize. And yet its pull keeps surfacing over and over. Galaxies whirl as though they hold vastly more mass than the stars and gas we can see could ever account for. Clusters bow the light behind them more sharply than their glowing matter on its own should manage. Even the vast patterns strewn across the whole cosmos settle into place best when some unseen substance is present, helping pull structure together. This is no minor footnote to tidy the numbers. By a broad margin, it seems to weigh more than all the ordinary matter combined. We still cannot say what it is built from, whether some quiet particle or something odder than we have dared to imagine. But the evidence inscribed in gravity is very hard to brush aside. Picture dark matter as an invisible scaffolding propping up everything we can see. We cannot lay a hand on the material directly, yet we can still follow how the universe wheels around it. Look hard at how galaxies turn, and the same hidden hand appears. Out along the far rims of spiral galaxies, the stars and gas travel at speeds that truly startled the astronomers who first clocked them. Were only the visible matter present, those outer reaches should ease along slowly, and some of it might not even hold itself bound at all. Instead, the rotation curves remain flatter than anybody anticipated, with stars distant from the center still tearing along quickly. The simplest answer is that each galaxy nestles within a vast, unseen halo of extra mass. That dark matter lends its gravity yet sheds no light at all, binding the whole thing together and guiding how it moves. That realization reshaped astronomy, because it told us the bright disk we photograph is not the entire galaxy. What our cameras gather is only the visible piece, seated inside something far larger we cannot see. And it does not hinge on one galaxy alone. The same pattern surfaces across countless systems. Every spinning disk turns into a quiet clue. Those outer stars are not merely circling beautifully, they are pointing steadily towards something hidden. Now I want to carry you to one of the oddest twists in all of this. Through most of the 20th century, plenty of scientists firmly assumed gravity would slow the expansion of the cosmos as the ages rolled by. Matter draws matter inward, so it felt only natural to expect that space, as it stretched, should gradually shed its pace. Then we observed distant stellar explosions, and they revealed something nobody was awaiting. The expansion was not simply continuing, it was picking up speed. To pin a name on it, cosmologists began calling it dark energy. Now, it is no ordinary substance, nothing anyone has ever scooped into a laboratory jar. It is merely a name for whatever drives this vast cosmic quickening. It might tie back to whatever energy lives inside empty space, or it might be hinting at new physics that lies past everything we now grasp. The discovery reshaped how we picture the universe's whole future. Gravity pulls matter together into galaxies and into clusters, yet out across the very largest scales, some other influence seems to keep nudging that expansion along. The cosmos is not merely drifting away from where it began. Something we cannot name appears to be altering its speed. And so, the universe stretches faster now than it did ages back. The light from remote objects holds within it a record of how space shifted while that light was making its way to us. By weighing distance against redshift, astronomers can reassemble the whole expansion history, and what they uncover is striking. In the earliest days, matter slowed things more firmly because everything sat nearer together and gravity stretched across the great regions more strongly. Later, as space spread wider and matter grew thin, whatever we name dark energy seized the upper hand. The expansion started to accelerate. This does not mean every single thing is rushing faster through the space right beside it. The galaxies and stars and planets close at hand, and you and I, remain governed mostly by local gravity and the ordinary forces about us. The quickening reveals itself only across enormous spans of the cosmos, where space stretching out on its own turns into the whole tale. The universe has, in a sense, changed its mood. It was once reined in by the pull of matter, and now, on its grandest scales, it is being driven ever onward. I'll leave you with an honest confession. We still cannot say what dark energy truly is. The name rings confident, yet it is really a placeholder we hold over a profound mystery. It accounts for what we observe, in that it suits this accelerating expansion neatly, yet its deepest nature stays veiled from us. Perhaps it is what we call the cosmological constant, a kind of energy woven straight into the fabric of empty space. And here is a thought I find soothing as the night settles in. This very emptiness once kept another secret. It is thought that roughly 380,000 years after the beginning, the universe cooled enough for light to finally roam freely, and the cosmos turned clear for the very first time. That ancient glow is still drifting through everything, the cosmic microwave background that Penzias and Wilson chanced upon in 1965, the faint afterglow of the world's first light. So, when we wonder what fills the dark between the stars, we are posing a question as old as light itself. Another possibility is that dark energy is some restless field that shifts and changes as time passes. We do not yet know. And there is something gentle in not knowing, a quiet room left ajar at the far edge of the cosmos. Let me stay beside you in the quiet a moment more, because one stranger notion deserves holding before we drift onward. It may be that gravity itself does not act the same way across the very widest stretches of space as our finest theory anticipates. That idea, I confess, feels comforting and unsettling all at once. Every such possibility leaves a mark of its own, and so those who devote themselves to these questions go searching, patiently, within exploding stars far away, within the manner that galaxies bunch up, within the way light bends as it passes weighty things, and within the dim old warmth lingering from the start. Up to now, the plainest picture has held together better than anyone dared hope. Yet holding together, let me softly remind you, isn't the same thing as genuinely grasping it. And this counts, because the stuff we name dark energy appears to constitute the bulk of all the energy that exists. The biggest single piece of this whole unfolding tale might be something we simply cannot put a name to. Only in 1998 did astronomers, studying faraway stars in the act of exploding, discover that the cosmos is swelling at a quietly quickening pace. So let this be a tender thought to settle on. We are able to gauge the heavens with great care and yet find them profoundly, gorgeously unknown. Now let me reveal to you the form of the whole thing. At the very grandest scales, galaxies do not lie strewn about like dust across a tabletop. They draw together, pulled into long, luminous threads, into wide sheets and tight knots, with great hollow gaps lying in between. The cosmic web is what astronomers name this, and to my mind, it ranks among the loveliest things they've turned up. It rose out of almost nothing, out of the faintest roughness in the young density of matter, gradually heightened by gravity across the ages. Dark matter set down the hidden framework to begin with, and everyday matter came along afterward, cooling and gathering into galaxies wherever the web drew taut enough. Where the threads cross sit the mighty galaxy clusters, like brilliant cities, with filaments running across them over gulfs so broad that light itself requires millions of years merely to traverse. Much of the web stays hard to glimpse at all, its gas thin and dim, so people chart it by where galaxies fall, by light that bends, and by the shadows that particular wavelengths leave behind in faraway starlight. What surfaces is among the grandest formations we are aware of. The cosmos, you understand, is no plain sea of galaxies. It is a linked network, carved by gravity over the long billions of years, its bright matter only outlining a concealed architecture below. Let me draw you nearer to those luminous crossing places, the clusters, since they are the biggest things gravity contrives to hold fast. One lone cluster might hold hundreds or even thousands of galaxies, drawn together and kept that way. Still, the galaxies are merely the portion you can lay eyes on. There is also tremendous hot gas, a glow in X-rays, and far more dark matter besides, which bears most of the heft. Within, the galaxies race through a shared pull at staggering speeds. A few smash into one another. A few are stripped of their gas as they hurtle through. The gas in between can rise to millions of degrees, so the chamber inside a cluster is anything but vacant. These clusters count because they rest where the web's threads pack most tightly, and their unhurried growth preserves a record of how all of this structure came into being. They likewise bend the light of objects behind them, enlarging the distant and the dim. Bigger patterns do stretch out beyond them, yet those tend not to be bound up as single steady systems. A cluster is a genuine cosmic city, drawn together and kept whole by gravity all on its own. And now the reverse, the vast emptiness lying between the threads, which can run for hundreds of millions of light years across. Among the bright filaments rest enormous zones with very few galaxies. They aren't perfectly bare, but alongside the clusters and threads they are thin and faint. Their extent is hard to picture. Some carry on across hundreds of millions of light years, ranking among the largest features to be found anywhere. The Bootes void is one such cavity, so immense and so very nearly stripped that it has long troubled the people who first took its measure. These voids hollowed out because matter eased away from the leaner places toward the fuller ones, so the rich swelled richer, and the bare grew barer still. Scientists lean on them to probe their notions, because how a void is shaped and spread hangs on gravity, on dark matter, on dark energy altogether. They are not empty pages. They belong to the pattern, and a void can teach you how the cosmos expands and how matter draws in. In this charting of the heavens, even absence carries structure and history and meaning. Let me ease back to the outermost limit of all we could ever witness. A horizon lies out there, past which our sight cannot stretch, and not on account of any wall blocking the path. It is purely that light from farther off has not yet had time enough to arrive. The cosmos holds a finite age, and light travels at a finite pace, and between them, those two truths carve out what gets called the observable universe. And since space stretched while that light made its crossing, the genuine present span to those distant zones runs far beyond what the travel time alone would imply. So the boundary is not the rim of everything that is, it is only the rim of what we are able to witness. Someone watching from a galaxy well past our horizon would possess their own observable universe, centered upon themselves, taking in a different slice of regions. I find that thought a humbling one. Our map is enormous, and even so, it is not the whole country. It is merely the portion that old light has contrived to bring us. The entire cosmos may be far vaster than any of this. Whatever lies past the horizon need not differ in nature. There could be more galaxies, more clusters, more empty stretches, carrying on much as they do right here. Or the greater whole might harbor features we have no means of reaching. Because no signal from those zones has yet come, sure knowledge is, for the present, out of reach. So scientists work from the shape of things, from how even and how outward the visible cosmos appears. The measurements reveal space sits very near to flat at the grandest scales, which might mean the whole is vast next to our little window, perhaps even without end. Should space genuinely carry on forever, then journeying outward would never deliver you to a final shore. There would forever be more lying ahead. This is tough for us, since everything we lay hands on has its edges. Rooms come to an end. Roads come to an end. Maps are drawn with borders. Space, perhaps, is not. And here is the most soothing part to drift off upon. The cosmos may possess no center whatsoever, and no outer rim. It need not be expanding into anything beyond itself, for space can merely alter its own scale, all over at once, with no central point from which everything flees. It might be finite and yet curved, lacking any boundary, the way Earth's surface has no edge, though its area stays finite. That ancient microwave glow, the cosmic background radiation that Penzias and Wilson came upon back in 1965, reaches us from every direction, astonishingly smooth. Very nearly the same warmth no matter where we turn. That sameness murmurs that the young cosmos was once remarkably uniform across colossal spans, and it stands as one reason the notion of inflation grew so dear to those who study how it all began. Listen with me a moment to that ancient glow, because it is not quite the same wherever you turn. Those faint unevennesses are everything. They mark the places where the early cosmos ran a touch denser, and the places it thinned a touch. And out of that gentle contrast, the whole cosmic web would one day unfold. Spacecraft have traced this light with astonishing care, turning the slightest shifts in warmth into a careful ledger of how all things stood when the universe was new. What I am holding up for you is not a portrait of stars nor of galaxies. It reaches us from a time before any of those had taken form. It catches the cosmos at a moment when matter and radiation still moved together, when the grand shape of all that was coming remained only the faintest hint. Let me sit with you on this because it matters. That eldest light holds a weave of warmer and cooler patches, and they are small, almost unimaginably so, yet they are no mere static. Within them lives the memory of density, of motion, of sound waves rippling through the hot young plasma. Wherever matter pooled a little more thickly, gravity found its foothold. Slowly, patiently, such places drew in more and yet more, becoming the seeds of galaxies and of great clusters. The thinner regions emptied away into the vast hollows, the voids. By reading this weave, those who study the sky can weigh how old the universe is, what it is made of, what shape it holds, and the long tale of how it has grown. It is, I think, among the richest single messages anywhere in science. Picture it less as a finished blueprint and more as a set of opening conditions, the starting marks from which gravity first began to build. And when astronomers lay this old chart beside the maps of galaxies we behold today, the agreement is quietly stunning. The immense architecture all around us rose out of those faint freckles in the earliest light the cosmos ever let slip free. Here is something I love to share when the night lies still. Every telescope is, in its own fashion, a device for peering backward, since light needs time to reach us. So whenever you look outward into space, you are also looking into an earlier hour. The more distant a thing happens to be, the longer its light has wandered before arriving at your eye. A nearby star you behold as it was a few years past. A far galaxy you behold as it stood billions of years in the past, or merely millions. And so the study of the heavens turns into a kind of history, one written in light itself. A telescope does not merely make far-off things larger. It gathers ancient light and keeps intact the look of things from the instant that light first set out. No vessel we could ever build can sail back through the years, yet light bears the past forward to us all on its own. When some instrument catches a faint whisper from the deep, it is receiving a letter that crossed an expanding cosmos for ages, and the telescope becomes a way to read time as surely as it reads distance. Let me bring you to one such instrument, because it has been remaking what we know. Built to gather infrared light with a tenderness no eye could rival, the James Webb Space Telescope earns its place here. That gift matters, you see, because cosmic expansion stretches the light of the most distant galaxies, drawing it out of the visible and ultraviolet and shifting it toward the infrared before it ever finds us. So Webb can peer through veils of cosmic dust, can study the dimmest among the early galaxies, and can examine how the stars glowed when everything was far younger. Its broad mirror and its cold, patient instruments let it sense signals that left earlier telescopes straining. And already it has shown us faraway galaxies in surprising, startling detail, raising fresh questions about how swiftly structure took shape, how such early light could already be so bright. It does not see the very first beginning, since there was a time before any star or galaxy at all. But it can gaze far back into that age when galaxies of the earliest generations were only beginning to rise. And in doing so, it turns the young universe from a theory written on paper into something we can truly witness. Those first galaxies, you should know, were smaller and far more unruly than the ones familiar to us. They rarely wore the calm, sweeping spiral forms you might picture from the usual images. Many were little, crowded, irregular, because they were still drawing themselves together. Gas lay everywhere, collisions arrived often, and sudden storms of starbirth could set compact regions ablaze with fierce energy. Across long ages, the smaller pieces fused, pulled in more matter, and swelled into larger forms. Some settled into disks, others were battered by collisions into rounder shapes. To watch these early galaxies is to catch that growth in the very act. Their light tends to reveal hot young stars, ragged outlines, and a chemistry less enriched than that of later times. They are not crude or backward, only young, systems coming together within a universe still raising its own architecture. Looking upon them feels to me like seeing a city before its roads are paved, before its neighborhoods have settled, before the skyline takes the shape we would know. The grown, settled cosmos rose out of these restless first attempts. And that brings us to the atoms themselves, growing richer with each generation of stars. The universe opened with only a few kinds of atom to its name. Stars changed all of that, through their living and their dying, returning enriched matter back to space. Many of the heaviest elements were forged in the violence of exploding stars and in the collisions of neutron stars, where gold and iron and so much else were scattered outward. Stars that came later formed from gas already carrying more complex elements than the ones preceding them. Astronomers name this rising abundance metallicity, and at heart, it tells the story of cosmic recycling. The eldest stars tend to hold the fewest heavy elements, while younger ones can carry mixtures far richer. This matters for worlds like ours, since a rocky body needs its oxygen and magnesium, its iron and silicon, all in the proper forms. It matters for life as well, which depends on sulfur and phosphorus, on nitrogen and carbon, and a host of other ingredients that stars make or scatter. Every stellar generation adds to the shared inventory. The cosmos did not turn chemically rich in a single stroke. It deepened in richness through cycle after cycle, each one a turn of birth and burning, of release and of renewal. And so, every newest star system holds within it some quiet memory of all the stars that lit the way before. Let me linger beside you a little longer, because the matter all around us holds something I find quietly moving. A lone atom of carbon may drift for ages, traveling out of the air into a leaf, settling down into soil, then escaping into the sea and circling back once more. None of this is freshly made. The ground beneath you, along with the body cradling you, is built of aged fragments, borrowed and reassembled. Our world is only a brief gathering of ancient stuff, endlessly reworking the pieces it was handed long before any of it took shape. And the glow you gather whenever you turn your gaze upward carries that very same depth of years. A star's shine may have departed before any city stood, before written words, before anyone scattered the first seeds. A few stars rest close enough that their light slipped away only inside the reach of recorded time. Others lie so remote that their light set out across a world far more ancient than our own. Whatever became of that star on its long path, the older message it once sent is what still reaches your eye. So in looking overhead, you do far more than peer into the distance. You are collecting signals from countless separate moments together, every pinprick of light an emissary from days gone by. That lends even the plainest stargazing a hidden gentleness. Using nothing but your eyes, beneath a genuinely dark sky, perhaps a few thousand stars come within your count, and that seems generous. Yet it amounts to almost nothing against the teeming crowd of our galaxy, let alone everything that lies beyond it. The greater part of stars are merely too dim, too remote, or curtained off by dust. Plenty are little red dwarfs that smolder faintly, much paler than the brilliant ones tracing those constellations you can name. And the air overhead narrows our view still more, as do the glows of our towns, as does our own seat lodged within the galactic disk. The stars familiar to us form only a tiny, nearby lopsided sampling, and never the full likeness of the Milky Way. Through a telescope, that opening widens, spreading star fields and clusters and faraway galaxies before us. Still, even the most penetrating pictures graze only minuscule shreds of the heavens. the blackness dividing the stars holds no true emptiness. Mostly, it marks the boundary of how far we can see. Out there waits far more radiance than our eyes were ever fashioned to take in. What I keep coming back to is the way such abundance arises from so meager a start. Matter is drawn inward by gravity. The forces of the nucleus mold the hearts of atoms. Electromagnetism governs light and chemistry and each charged thing. Out of those few unremarkable laws came clouds and stars and worlds, oceans and minerals, and, eventually, living cells. The young cosmos had no need to begin already complete. All it required was a setting in which structure could ascend on its own terms. Faint unevennesses ballooned into sweeping patterns. Plain atoms were welded into weightier ones within stars, and the gold in a wedding band, the iron coursing through your blood, were flung outward by stars that burst apart and by neutron stars in collision, born inside the fiercest furnaces this cosmos has ever kindled. Through unhurried impacts and unwearying gravity, dust turned into worlds. And upon at least one little world, chemistry turned into biology, and biology by some route turned into awareness. That any of this came to pass renders it only more wondrous, never any less. Complexity is nothing apart from physics at all. It is simply physics, once-handed time and energy, and the opening to build. I'd like to trace that opening softly toward the distant future, since the making cannot go on without end. To spin fresh stars into existence, galaxies require chilled gas, and that supply is gradually consumed, warmed, driven off, or sealed within bodies that endure for ages. In the eras ahead, the rise of new stars may turn scarce, kindling only where some final cloud is able yet to cool and tumble together. A collision between galaxies might rouse new material. Aging stars might give back a trickle of gas, but the tally will shrink. The thinking goes that the closing generations may consist largely of small red stars, which call for scant mass and can smolder across nearly unthinkable reaches of time. They would burn in a cosmos by then more aged, dimmer, more thinly scattered than ours, like the final handful of candles drawn from the remnant fuel of galaxies. Astronomers hold that the universe may someday harbor nothing but dwindling remnants. The luminous era of stars will go by. First, the towering stars die away, then the mild sun-like ones, and finally, the enduring red dwarfs, after reaches of time the mind can hardly grasp. What stays behind may be white dwarfs and neutron stars, black holes, frozen planets, and scattered wreckage. Galaxies grow faint as their radiance gradually deserts them. Certain remnants wander off into the depths, cast loose by chance meetings. Others keep circling within their darkened systems. Across far vaster ages yet, even black holes may waste away. This is what some name the heat death, or the big freeze. No abrupt finish whatsoever, merely a long, hushed dimming as usable energy becomes ever harder to draw together. The cosmos would remain. It simply would no longer blaze as it does at present. And that, oddly enough, is exactly what makes this moment the two of us share feel so precious. We are here while the stars are still alight, while galaxies are still aglow, while the universe stays bright enough, for a brief spell, to gaze upon itself and marvel. And here, I think, is where I'll let you rest. We have come a long way together tonight, out past the first light and the dying of stars, past the bending of time and the great dark we may never fully name. There is nothing further you need to follow now, no distance left to cross, no question still asking to be held. Let the galaxies drift on without us, slow and silent and unhurried, the way they always have. Let the vast quiet settle over you like a blanket of stars. Breathe in, slow and deep, and feel how small and safe you are beneath all that ancient light. Breathe out and sink gently down, past every far and shining thing, into the warm dark below all thought. The journey is over now, and you are exactly where you should be. Sleep well and drift easy, and let the night carry you the rest of the way home.